Surface integrals are difficult. Let's do that kind of problem. Computing the normal component of the curl over a surface. First off, compute the curl. If it's 0, the problem's finished. Hiding the first column, determinant of the other two. Second column hide. And third column hide. So we're going to actually have to compute because it's a non-zero curl. Look at our surface. There's our R-squared group, so ZR plane's a natural place to draw this. Upward facing normal, standard orientation. Parameterize our surface. Plug in the equation first. Polar coordinates, so it's sine and cosine. Two variables, surface. When we compute this cross product, we got to make sure that the z component is positive, so that's the correct way. Take our r derivatives, theta derivatives, cross them, sine squared plus cosine squared is 1, so that reduces. Z component positive, so this is the correct normal. Plug in our parameterization, our parameter domain. R is 0 to 2, and theta is unrestricted. Plug the parameterization into F. There is nothing to plug in. Do our dot product. And compute. I'll do the theta integral first, because there are no thetas inside. Eight pi. Now let's use Stoke's theorem. Redrawing our surface. There's our boundary. R is 2, Z is 2 squared, 4. Two equations, that's a curve. Upward normal, right-hand rule. Using cosine and sine for x and y, that is the standard orientation. So our derivative is going the right direction. Plug in our parameterization. Plugging in for y, plug in for x, plug in for z. And dot it with our TDS. Sine squared plus cosine squared is a 1. And I'm integrating 4 over the interval, so it's 8 pi. Finally, using the divergence theorem, redrawing our surface, I'm going to want to think of another surface I can put on here to enclose a region. If I reverse the orientation and then close off the top, that'll make a region that's fairly simple. And the nice thing is this new surface I've added is really simple. Call it B, or be nice. I've reversed the orientation of the normal. Normal for the surface B is just the k vector. B, the equation for it is z equals 4, and so it's a disk of radius 2 at height 4. This is then the divergence theorem, the divergence of the curl. That's always 0, but let's compute it just for practice. So my two surface integrals equal 0. I'll take my surface integral over S to the other side, which flips the sign on the normal. Curl f dot k is 2, so it's 2 times the size of the disk. The disk is pi r squared, 8 pi.